Analyzing the graphs of nonlinear functions. A graph of a function is a visual representation of how the dependent variable, usually y, depends on the independent variable, usually x. The graph is a collection of points x and y that satisfy the function's equation. We have seen how to graph equations and seen that functions are also equations where y equals f of x. We can now look into reading and analyzing the graphs of nonlinear functions. Now let's turn our attention to the graph to answer questions about a function. Suppose f is defined by this graph here. Example number 1. What is f of negative 2? Here's the answer. The input is negative 2. We find negative 2 along the horizontal axis and then search vertically to find the point on the graph. The point is negative 2, positive 3, and we conclude that f of negative 2 is equal to 3. So once again, we look for the input, which is negative 2. We search for that along the horizontal axis, also known as the x-axis. And then we look vertically up and down from negative 2 to see where the x input matches the graph, which is up here at y equals 3 along the horizontal axis. So we conclude that f of negative 2 is positive 3. Example number 2. What is or are the solution or solutions to the equation f of x equals 2? Now, the output is 2, and we find 2 along the vertical axis, also known as the y-axis. Then search horizontally to find all the points that form something with 2 in the y-coordinate. There are 3 points, negative 4, 2, negative 1, 2, and 3, 2, and 3 solutions, x equals negative 4, negative 1, and 3. Since in this case 2 is the output, we're going to search along the vertical axis or the y-axis. So we go here where 2 is the output, 2 is the y-coordinate, and we look horizontally along this line. And we see that there are 3 spots that intersect the line, when x is equal to negative 4, when x is equal to negative 1, and when x is equal to positive 3. So as we stated, there are 3 points, negative 4, 2, negative 1, 2, and 3, 2. So the solutions are going to be just the x-coordinates, negative 4, negative 1, and 3. Example number 3. What is the domain of f? Let's take a look at the graph and determine the domain. Here's the answer. We can determine the domain by projecting all of the graph onto the x-axis. Moving from left to right along the horizontal or x-axis, we discover that the domain is negative 4 less than or equal to x, which is less than or equal to 3, as shown on the green line. In other words, the domain is all the numbers between negative 4 and 3 inclusive. If we look at the graph, starting at the far left x value, right here, and going along the x-axis or horizontal axis till we get to the other end of the graph, we see that the x values start at negative 4 and stop when we get to positive 3. And again, we are looking at just the x values. That's the domain. Example number 4. What is the range of f? So let's take a look at this graph and determine the range of f. So remember that the range is all of the y values, the values along the vertical axis or the horizontal axis. Generally speaking, it is the list of output values. So we can determine the range by projecting all of the graph onto the y-axis. Moving from the bottom to the top, we see that the range is negative 2 less than or equal to f of x, which is less than or equal to 3, as shown on the green line. So f of x is representing our function. Also remember that f of x is synonymous with y. So we look at the lowest value right here occurs at negative 2, and the highest value of the graph occurs right here at 3. So f of x, all the y values, are all of the values starting at the lowest, negative 2, and going up to the highest, which is positive 3. And we have determined the range. Example number 5, we want to determine the maximum value of f. So by looking at the graph, what is the maximum value? The maximum value is the largest number in the range. So the maximum value is the largest number in the range. And since the range goes from -2 to +3, the maximum value in that range is at 3 right here. If you think of this as using geographical terms, mountains and valleys, the maximum value would be the peak of the highest mountain, which is right here at y equals 3. Notice the notation. We also say the f of max. Using our function notation, we say f is the function using the subscript max, and then we tell the actual value is 3. Example number 6 asks the question, what input minimizes the value of f? And here's the answer. The minimum value is the smallest number in the range. Since the range goes from -2 to +3, the minimum value in that range occurs at -2. This is achieved at the input x equals 1. So again, the minimum is the smallest value along the range. Okay, so we're looking at all the f of x values or all the y values. And that occurs, the smallest number in the range is at -2. Now, here's the smallest numbers at -2, but we're asking for the input value. And the input value is x equals 1. That's the value that makes the function hit the lowest point. Going back to our geography analogy, if we're driving along and we're looking at mountains and valleys, and this is the road, at what mile marker would we see the lowest point of the valley? And it would be at this mile marker right here. Now, again, our analogy, we're assuming there's negative mile markers, but I'm just illustrating a point. We're driving along, and we're using the horizontal axis to see what input gave us the lowest point of the function. Practice number 1. Given the graph of f, we're going to ask you to do 3 things. A, evaluate f of 1 plus f of 5. B, solve for x when f of x is equal to 0. And C, how many solutions are there for the equation f of x is equal to 5? So pause the video, find the answer to these 3 questions, and then resume watching the video. And welcome back. Let's take a look at part A. For part A, we need to determine the value of f of 1. F of 1 means that when x is equal to 1, the value of f is up here, and that occurs at 8. So this is the point 1, 8. That's where we get 8 from. Now f of 5, we go here when x is equal to 5, and that's where the function crosses the x-axis, so the value of f of 5 is 0. So evaluating f of 1 plus f of 5 is the same as saying 8 plus 0, or 8. For part B, where f of x is equal to 0, we want to solve for x. F of x equal to 0 is the output value for the input of 3 spots, 0, 3, and 5. So the line crosses the x-axis when x is equal to 0, when x is equal to 3, and when x is equal to 5. So these are the 3 values of x, which will make f of x equal to 0. For number 3, we want to know how many solutions there are when f of x is equal to 5. We don't know what the solutions, we just want to know how many. So I'm going to draw a vertical line where f of x is equal to 5. I'm sorry, I mean a horizontal line. So I added a vertical line at f of x is equal to 5, also known as y is equal to 5. And I noticed that the line crosses the function 3 times, here, here, and here. So there are 3 solutions for f of x is equal to 5. Practice number 2. Consider the graph of f of x is equal to x squared plus 4x plus 1. What is the domain and what is the range? So take a look at the graph, pause the video, determine the domain and range, and then resume watching the video when you have your answers. Welcome back. Let's see how you did. Graphically speaking, this graph extends forever. It's an infinite graph from negative infinity to positive infinity. So as we go along the x-axis here, going off to negative infinity, all the values will be covered by the graph. As we go to positive infinity, all of these values on the x-axis will be covered by the graph of f of x. So we say the domain is from negative infinity to positive infinity. A word about notation. Notice I am not saying less than or equal to, less than or equal to. Okay, that's not the case. You cannot equal infinity. So f of x can be, or I should say negative infinity is less than f of x, which is less than positive infinity. But you can't underline them to include them. So just a word about notation. Also, algebraically, if we think about restrictions on the domain, there are no restrictions for this function. You don't have to worry about a zero in the denominator. You don't have to worry about a negative under the radical. So because there's no restrictions on this function, there's no restrictions on the domain. So the domain will go from negative infinity to positive infinity. Now let's turn our attention to the range. The lowest value of the range occurs right here when y, or f of x, is equal to negative 3. Now from this point it goes up to infinity. So we would say that the range has the lowest value of negative 3, and we can include that. So you notice it says less than or equal to. So we have f of negative 3 is less than or equal to f of x, which is less than infinity. Increasing and decreasing intervals. A function is increasing on an interval provided y increases as x increases for all x in that interval. A function is decreasing on an interval provided y decreases as x increases for all x in that interval. So as we take a look, as x starts at 0 and we increase going from left to right, x is getting bigger. Look at the function. The function is getting bigger in value. The numbers are getting larger and larger. It's going uphill from left to right until we get to this point. Once we get to this point, we notice the function begins to get smaller. It's decreasing. It's going downhill. The y values are getting smaller. So while y increases and then decreases, x is always increasing. We always measure whether or not a function is increasing or decreasing based on the y values. X will always be increasing as we measure that. Example 7. On which interval or intervals does the function f decrease? The answer is the function decreases for those numbers x where the graph is downhill from left to right. Therefore, the graph decreases for negative 2 less than or equal to x, which is less than or equal to 1. So if we look at the x values from negative 2 to 1, we notice that in this range here, this graph is going downhill. Therefore, it's decreasing. Now let's talk about positive and negative function values. A function is positive in value for all x where its graph is above the x-axis. A function is negative in value for all x where its graph is below the x-axis. So I am going to insert a dotted line along the x-axis. Everywhere the graph is below this line, below the x-axis, you'll note it's highlighted in red. These are negative values for the function. Everywhere the graph is above the x-axis, it's highlighted in blue. It's shaded in blue. Those indicate positive values. Now note the difference between the positive and negative function values versus increasing and decreasing. Increasing and decreasing refers to the direction at which the graph is running. Positive and negative values refer to its position on the graph relative to the x-axis. Example number 8. On which interval or intervals is f of x less than 0? Let's talk about the notation f of x is less than 0. Numerically, this is a way to say that the number values are negative. Now, graphically, that's referring to the region below the x-axis. So we're talking about below the x-axis, not including the x-axis, but below the x-axis. Remember, the x-axis itself is the line y equals 0. So we can't have a line sitting right on the x-axis because the function f of x would equal 0, and 0 is not positive or negative. Let's go to the next slide and take a look at the answer. So you'll see I highlighted in green the interval right here. It's a green V with open circles at 0 and 2. And here's what the answer is. The function is negative in value for those numbers x where the graph is below the x-axis. Therefore, the function is negative for x between 0 and 2. And the reason why you'll see it's not including 0 and 2, in other words, it's 0 less than x, x less than 2. We're not saying less than or equal to because the point at 0, the graph is actually on the x-axis. That's not less than 0. Same thing when x is equal to 2. That point is on the x-axis. It's not less than the x-axis or below it, so we can't include that as well. That's why we have an open interval. Example number 9. On which interval or intervals is f of x positive in value and increasing? So when we are talking about positive in value, we are referring to the region above the x-axis. And when we are talking about increasing, we're talking about the portion of the graph where it goes uphill from left to right. Let's take a look at the answer. The function is positive in value and increasing for those numbers x where the graph is uphill and above the x-axis. This is true for -4 less than or equal to x, which is less than or equal to -2, and 2 less than x, which is less than or equal to positive 3. Let's look at this in a little more detail. For this first interval here, where x is between -4 and -2, inclusive, because we're including the endpoints, we notice that the graph is completely above the x-axis. But the reason why this portion is highlighted in green is it's also increasing. Anything after x equals -2, the function is decreasing, so we're not including that. The second portion is x is between 2 and 3, including 3. So the x values would be right here. That would be the domain. And the reason why 2 is an open circle is because when x is equal to 2, the function is 0. It's on the x-axis. 0 is neutral. It's not positive or negative, so we're not including it. It's just an endpoint. But you'll notice that this portion of the function is highlighted in green because not only is it positive, but it's also increasing.